Welcome, everyone, to our Parasitology lecture. Today, we are diving into the fascinating and dangerous world of Schistosoma haematobium. This microscopic parasite is responsible for a devastating tropical disease that affects millions of people worldwide. By the end of this session, you will understand how this parasite infiltrates the human body, the severe damage it causes to the urinary system, and the mathematical tools epidemiologists use to measure and combat its spread. Let us begin our journey into the life of the blood fluke. Now that we know what we are studying, let us look at how the infection begins. Imagine taking a refreshing swim in a calm, freshwater lake. Unbeknownst to you, thousands of microscopic, fork-tailed larvae called cercaria are swimming in that exact same water. They do not need to be swallowed. When they find a human host, they simply dissolve a tiny hole in the skin and slip right into the bloodstream. It acts like a stealthy hijacker, navigating through your veins until it sets up a permanent home in the blood vessels surrounding your bladder. Having seen how it enters the body, let us explore the biology of this unique creature. In scientific terms, Schistosoma haematobium is a digenetic trematode, which is a type of flatworm. The word digenetic is crucial here. It means the parasite requires exactly two different hosts to survive. It uses a specific freshwater snail as its intermediate host and a human as its definitive host. Furthermore, unlike most flatworms, which are hermaphroditic, these schistosomes have distinct male and female sexes. Once inside the human blood vessels, the male and female pair up and live together in a constant, lifelong embrace. With the adult worms settled in the body, we must understand the damage they cause. The paired worms specifically target the venous plexus, a network of veins surrounding the urinary bladder. The real danger does not come from the worms themselves, but from their offspring. The female releases hundreds of spiky eggs daily. To leave the human body, these sharp, terminal-spined eggs must physically pierce through the bladder wall so they can be excreted in the urine. This violent tissue damage causes the hallmark symptom of the disease, hematuria, which simply means visible blood in the urine. This microscopic damage leads us to a massive global health crisis. Schistosoma haematobium is responsible for urogenital schistosomiasis, a devastating tropical disease affecting over 100 million people, primarily in sub-Saharan Africa. If left untreated, the constant bleeding leads to chronic anemia. The structural damage causes severe kidney issues and irreversible bladder scarring. Even worse, many of the spiky eggs never make it out of the body. They get trapped in the bladder wall. The chronic inflammation caused by these trapped eggs is a major leading cause of squamous cell carcinoma, a deadly type of bladder cancer. Before we move on to diagnosing the disease, let us visualize this entire process. Here you see the complete life cycle of the parasite. Starting at the bottom, infected humans excrete spiky eggs into fresh water through their urine. These eggs hatch into ciliated larvae called miracidia, which swim and infect the intermediate host, the bullinus snail, shown on the right. Inside the snail, they multiply and transform into fork-tailed cercariae. These cercariae leave the snail, swim through the water, and penetrate the skin of a new human host, shown at the top, completing the deadly cycle. Now that we understand the life cycle, how do doctors measure how sick a patient is? Simply knowing a patient is infected is not enough. We need to measure the intensity of infection. This formula standardizes the severity of the disease. I represents the intensity, measured in eggs per 10 milliliters of urine. E is the total number of eggs counted under the microscope, and V is the volume of the urine sample provided. We multiply by 10 to scale the result to a 10 milliliter baseline, which is the international standard. If the egg count E increases while the volume V stays the same, the intensity increases, indicating a much heavier and more dangerous parasite burden. Let us see this formula in action with a concrete example. A 12-year-old boy comes to a clinic with visible blood in his urine. The doctor collects a 25 milliliter urine sample, and the lab counts exactly 120 spiky eggs. We need to find his standardized infection intensity. First, we substitute our known values into the equation, dividing 120 by 25. This tells us there are 4.8 eggs in every single milliliter of urine. Finally, we multiply by 10 to standardize the measurement. The final answer is 48 eggs per 10 milliliters. Since the threshold for a heavy infection is 50, this boy has a moderate but dangerously high infection, requiring immediate medication. Having diagnosed an individual, we must now zoom out to look at the bigger picture. Public health teams often need to evaluate entire villages located near infested lakes. Instead of testing everyone, they test a random sample of children to gauge the community's health. To understand the scale of the crisis, epidemiologists look at two key metrics: the prevalence rate, which tells us how widespread the disease is, and the average burden, which tells us how sick the infected people are. If these numbers are high, it indicates a severely contaminated water source, meaning mass drug administration might be urgently required for the entire village to prevent an outbreak. To understand how widespread the parasite is, we use the prevalence rate formula. Conceptually, this is simply finding the fraction of the tested population that is sick and converting it into a percentage. In this equation, P stands for the prevalence rate, C represents the number of positive cases identified, and T represents the total number of people tested in the sample. We divide the positive cases by the total tested and then multiply by 100 to get our percentage. If the number of positive cases increases while the total tested remains the same, the prevalence rate shoots up, warning health officials that the parasite is spreading rapidly through the community. Let us apply this prevalence formula to a real-world scenario. A public health team visits a village of 500 people and tests a random sample of 40 children. Out of these 40 children, 15 test positive for Schistosoma haematobium. We want to find the prevalence rate. We plug our values into the formula, dividing the 15 positive cases by the 40 total children tested. This gives us a raw decimal fraction of 0.375. Multiplying by 100, we get our final answer, a prevalence rate of 37.5%. This is an alarmingly high rate for a single community, highlighting a severe breakdown in sanitation. Knowing that 37.5% of the children are infected is helpful, but we also need to know how severe their infections are. This brings us to the average infection intensity formula. Conceptually, we are pooling all the parasites found and distributing them evenly across the sick children to find the typical burden. II represents this average intensity. E total is the massive combined pool of all eggs counted from every positive patient. C is the number of positive cases. Because field teams often collect exactly 10 milliliters of urine from each child, the volume is already standardized, saving us a step. An increase in total eggs means the average child is suffering a much heavier parasite load. Let us finish our evaluation of this village by calculating the average burden. We already know there are 15 positive children, and each provided the standard 10 milliliter urine sample. The lab reports that the total combined egg count across all 15 children is a staggering 3,000 eggs. We substitute these values into our formula, dividing the 3,000 total eggs by the 15 infected children. The final answer is an average intensity of 200 eggs per 10 milliliters of urine. Since anything over 50 is considered a heavy infection, this massive number tells the medical team that these children are at severe risk for kidney failure and require immediate, aggressive treatment. We have covered a lot of ground today, so let us review the most important ideas. First, Schistosoma haematobium is a dangerous blood fluke that relies on a two-host life cycle between freshwater snails and humans. Second, the severe symptoms, including blood in the urine and bladder cancer, are caused by the female's spiky eggs tearing through the bladder wall. Finally, we learned how to use mathematical formulas to standardize infection intensity and calculate community prevalence. Understanding both the biology and the epidemiology of this parasite is the crucial first step in eradicating this disease from vulnerable communities worldwide. Great job today.